Welcome. This is the sixth lecture about conventional hemodialysis, about hemodialysis adequacy and dose. In these lectures, we are discussing the different chapters of the book Nephrotube Synopsis of Conventional Hemodialysis. You can check the previous 5 lectures on our YouTube channel. In the description of this video in YouTube, below the video, you will find some important links. The first link is a link to this same lecture, but in Arabic language, for those who like to watch the lecture in Arabic. You will find also a link to the playlist of video lectures about this book. You will find the link for the English playlist and Arabic playlist. You will find link to download this book for free. You will find link to download the PDF of this lecture for free if you like to use it. You will find a link for my website Nephrotube, nephrotube.com, where you will find more lectures about nephrology than hemodialysis lectures. And finally, you will find a link to Nephrotube social media accounts, the WhatsApp group, the Telegram channel, the Facebook group. You can join us to be always updated by the activities of Nephrotube. And finally, it's better to subscribe to our channel and to make the notifications on from our channel, so you will be notified once we upload new lectures. First, I want to highlight what are the targets to achieve optimum hemodialysis. Actually, we have a lot of targets that we have to achieve to get an optimum hemodialysis. We have about 16 points as to target that the patient will have good well-being, that the dialysis will not interrupt the patient's social life and job, adequate ultrafiltration to maintain residual kidney function, blood pressure, anemia control, calcium phosphate product control, control of acidosis, absence of intradialytic and interdialytic symptoms, short dialysis recovery time, no need for hospitalization, good vascular access with no complications, controlling the inflammatory state, lack of malnutrition, and finally, a good hemodialysis dose. So what I want to highlight here, that achieving a hemodialysis dose, a good hemodialysis dose, this means we have adequate hemodialysis. When you achieve a hemodialysis dose within the recommended target, we said that we have adequate hemodialysis. So to have an adequate hemodialysis is part of having an optimum hemodialysis. So achieving a good hemodialysis dose alone is not sufficient for a good health for our patient. Achieving a hemodialysis dose is a point of 16 points to get an optimum hemodialysis, and this is an important point that I want to highlight. From these 16 points, I discussed in my book, Nephrotube Synopsis of Conventional Hemodialysis, the point 15 and 16 in details. The other points are out of the scope of the book. I discussed how to assess the nutritional status of the patient through what is called normalized protein catabolic rate, and for sure the main concern of this chapter is to discuss how to test or to measure the dialysis dose. Let's start by this point. What is the normalized protein catabolic rate and how it assesses the nutritional status of the patient? Normalized protein catabolic rate is a marker of dietary protein intake and nutritional status in stable dialysis patients. It is usually established from the urea generation. It depends, the normalized protein catabolic rate normally depends on the urea generation rate. The main concern about the normalized protein catabolic rate, it's pitfall that if there is muscle breakdown or any factor that affect urea generation, it will affect the normalized protein catabolic rate. So normalized protein catabolic rate is not an accurate indicator, is not always an accurate indicator of protein consumption, and is not always an accurate indicator for the nutritional status, because it can be affected by urea generation, which has many factors affect it, and also if there is muscle breakdown due to any reason, will give high normal protein catabolic rate, although the patient protein intake may be lower in this case. The accepted value in stable hemodialysis patients of normalized protein catabolic rate is to be more than 1 gram per kilogram per day. It is well known that patients with high normalized protein catabolic rate have lower incidence of morbidity. How to calculate normalized protein catabolic rate in our patients? Actually, you can use this website where it contains calculators by Professor Dugerdas, the author of Handbook of Dialysis. In the website ureakinetics.org, you click here on solid solver light single patient calculator, and you can use this username and password. This is legal. The username is solid and the password is solver. Then it will open for you this calculator. In this calculator, on the top, you will find the days of the week. Before every day, there is a checkbox, and after every day, there is a multiple choice circle. Before the day in the checkbox, you will check the days of dialysis. For example, here, this patient has dialysis on Monday, Wednesday, and Friday. And the circle after the days, you will check the day where the labs were done. For example, here the labs were done for this patient on Wednesday. Then you have to fill this data. Let's take an example. Let's say that this patient name is Mr. Here, TRU, you put the residual kidney function. I put it here as 0. What is residual kidney function and how to calculate it? This will be discussed at the end of the lecture. How to calculate residual kidney function if the patient still having residual kidney function. How to calculate this residual kidney function to put it here. Then I considered here that this patient has no residual kidney function, so it is 0. Pre-blood urea nitrogen, let's say it's 150 in this patient. Post-blood urea nitrogen 40. Blood flow rate 300. Dialysate flow 500. Here we put the total duration of one hemodialysis therapy. Let's say the patient is dialyzing for 4 hours, so the total duration of the hemodialysis session is 240. Here the pre-weight of the patient, pre-weight for dialysis is 80 kg, and post-weight is 77, and the mass transfer coefficient area of the filter we used in this hemodialysis session is 1200. Then you press calculate. This calculator will give you a lot of data. All these data we will need in this lecture, and I will use this calculator multiple times in this lecture. But one of these data is the normalized protein catabolic rate. This patient has a normalized protein catabolic rate of 2.49, and this is good and within the target. Then next we will discuss achieving a hemodialysis dose within recommended targets. How to measure the hemodialysis dose? Actually, it depends on the uremic toxins removal. If the dialysis removed a lot of the uremic toxins, so the dose of hemodialysis is good, and vice versa. The uremic toxins are classified into three categories: low molecular weight as urea, middle molecular weight as beta-2 microglobulin, and the protein-bound uremic toxins as indoles and phenols. Which one of them is usually measured in hemodialysis to measure the hemodialysis dose? Actually, it is urea, although it has a lot of limitations that we will mention later, but urea is the preferred marker because of its ease of measurement, regular testing, well-known metabolism and generation rate, and also well-known volume of distribution, although it has a lot of limitation. So our lecture from now will go to mention how to test hemodialysis dose, again, which is a part of how to achieve optimum hemodialysis. So my talk outline from now is to cover point 16, which is hemodialysis adequacy and dose. We will discuss two main points in this lecture. First, methods to measure hemodialysis dose depending on urea clearance. Then we will talk how to measure and calculate residual kidney function, which is also known as residual urea clearance. Regarding first point, we'll have sub-categories below it. What are the methods to measure hemodialysis dose depending on urea? We have the main method, which is KT over V urea, and the other methods rather than KT over V urea. Below each of them, there are a lot of methods, and we will go step by step through each of these methods. Let's start by KT over V urea. Before going the different types of how, or different methods of how to measure KT over V urea, I have to mention again that KT over V is the most frequently applied measure of hemodialysis dose, although it has a lot of limitations that I will mention later. The second point that I mentioned a lot till now, that measuring the dose of hemodialysis is not an indicator that we got an optimum hemodialysis. It is a part of optimum hemodialysis. So a good hemodialysis dose is not always equal optimum hemodialysis. To get an optimum hemodialysis, we have to achieve all other targets that we mentioned in the 16 points, as control anemia, CKD, MBD, so on. Okay. To measure KT over V urea, the first equation is what is called the prescribed KT over V urea. Actually, we not use prescribed KT over V urea, but we have to mention it. Why we not use it? Why we are not using it? Because prescribed KT over V urea is an in vitro calculation of the dialyzer, of the KT over V of the dialyzer, by the manufacturer in vitro outside the patient body, and you will find it in the pamphlet or brochure of the filter. And always the prescribed KT over V urea will be higher than the actual delivered KTV of the patient. The in vitro, the delivered KT over V is the in vitro KT over V that I will discuss later. So the prescribed is always higher, and you can remember that we mentioned always in a previous lecture that most of the numbers calculated by the manufacturer are higher than the actual numbers in the patient. For example, before we mentioned that the dialyzer clearance that is mentioned by the manufacturer in vitro was always higher than the actual dialyzer clearance inside the patient's body. We mentioned that in the lecture of the dialyzers. Okay, we mentioned that we will measure now KT over V. What is KTV? K is the dialyzer clearance of urea, and we mentioned before what is dialyzer clearance exactly in the lecture of dialyzers. T is the dialysis time in minutes, duration of the dialysis session in minutes. V is the volume of distribution of urea. The volume of distribution of urea, how to calculate it? V, volume distribution of urea, equal 0.6 times body weight. You can see that the volume distribution of urea equation is the same equation we use to calculate the total body water. This is because urea is a small molecule. The small molecular weight of 60 dalton allows it to move easily between intracellular and extracellular body compartment, and this makes urea concentration equals in both intracellular and extracellular compartment. That's why the volume distribution of urea is equivalent to the volume of water in body. So that's why we use to calculate the volume distribution of urea, we use the same equation of total body water. Let's take an example. If a patient has body weight of 70 kg, is dialyzed for 3 hours, and by the way, if the version of the book that you have is written in it here 4 hours, please correct it to 3 hours. So if the patient body weight is 70 kg, this is in page 57. If the patient body weight is 70 kg, dialyzed for 3 hours, and the urea clearance, which is the K, is 30 ml per minute. Then KT, the K is the clearance. The clearance is 300. T is the time. We said that 3 hours. 3 hours means 180 minutes because we have to put T in minutes. Then the KT is about 54 liters. Regarding the V equal 0.6 times body weight. So V of the patient will be 0.6 times 70. Again, in your book, if you have the version where here is 80, please correct it to 70 in the same page. So 0.6 times 70 equal 42 liters. So we have now the KT and V. By dividing KT over V, it will be 1.28, which is approximately 1.3. So what is meant by KT over V is 1.3. This means that the total body fluids is cleared within the dialysis session 1.3 times. And if the KT over V is 1, this means that the total volume of body fluids is cleared only once during the hemodialysis session. If it is 2, if KT over V is 2, this means that the total volume of body fluids is cleared twice, 2 times during the hemodialysis session, and so on. Again, prescribe KT over V to only consider the dialysis clearance of urea, duration of dialysis, and volume distribution of urea, but it doesn't include ultrafiltration volume. So this is one of the pitfalls of this equation, and at the same time, one of its pitfalls that it calculates the KT over V in vitro, and always higher than delivered KT over V, and we never use it. It is just one of the criteria of the filter in the brochure. But what we must measure to our patients frequently in our hemodialysis session is the actual delivered KT over V. To calculate KT over V, there are three ways. Before going through them, I have to mention that delivered KT over V is the in vivo calculation of KT over V. The second, that the delivered KT over V will be lower than the prescribed KT over V that we mentioned in the last slide. And the third point, before going the different steps of how to measure delivered KT over V, we have to discuss first or describe first the urea movement post-dialysis. Let's go first through the urea movement post-dialysis before how the urea behave post-dialysis. How the urea behaves post-dialysis before we are going through the different methods to measure delivered KT over V. Let's suppose that this patient has serum blood urea nitrogen of 90 milligram per deciliter, and this is the extravascular compartment. Then after dialysis, immediately after dialysis session, the blood urea nitrogen decreased from 90 to 25, and for sure the extravascular pool urea also will be decreased. So if you take a blood sample from this patient immediately post-dialysis, you will find that the serum blood urea nitrogen will be 25. But if we wait for 30 to 60 minutes post-dialysis, some of the urea in the extravascular pool will diffuse to intravascular pool, and the blood urea level will be elevated from 25 to 40 milligram per deciliter. So it is important for us when we will take the blood sample of the patient, because if we took the blood or if we take the blood sample immediately post-dialysis, we'll have low blood urea nitrogen, and this will give you a high adequate dose of dialysis. But if you wait for 30 to 60 minutes, the blood urea in the blood will be higher, and this will make the dialysis dose to be lower. So we have to put this in mind while we are talking about the equations that I will mention now. We have to put in mind that we have two pools affect the serum blood urea nitrogen level. It is not one pool, it is not only the blood. We have two pools affecting this part, the extravascular pool and the intravascular pool. Because the urea in the extravascular pool after some time will move and will raise the urea level in the intravascular pool. So it is not only one pool which is the blood affecting the urea level, it is two pools. Now we will talk about different methods to calculate delivered KT over V. All these methods will be calculated by the same calculator I mentioned at the beginning of the lecture, which is ureakinetics.org. It will be easy to calculate all of these. Let's go now through the first method to calculate delivered KT over V, which is single pool KT over V. Single pool KT over V. To calculate single pool KT over V, we need the following data. We need the pre-dialysis blood urea level of the patient, the post-dialysis blood urea immediately at the end of dialysis, and this is an important point that I will highlight now. We need the ultrafiltration volume, which is the difference between the pre-dialysis weight and the post-dialysis weight of the patient, and we need the dialysis session duration in minutes. Why it is called single pool KT over V, and what is its main pitfall? We mentioned here that we will measure the post-dialysis blood urea immediately after the end of dialysis. So this method neglects that we have two pools affect the urea level. That's why it is called single pool, because we mentioned that there is a difference in the serum urea level immediately post-dialysis and 30 to 60 minutes after the dialysis. So it is called single pool as it measures urea level only in one pool, which is the blood, neglecting the effect of the second pool, which is the extravascular pool on the blood urea level. That's why this method, single pool KT over V, will overestimate the delivered dialysis dose, because it measures the lowest serum blood urea nitrogen after the dialysis. So it will give you a high dose or high adequate dose of hemodialysis. There are multiple equations to calculate single pool KT over V. I will just mention them. This is the first formula, and these are the abbreviations from the data we collected from the patient and the hemodialysis session. And this is the second formula. The second formula is the same as the first, but here you will find that we use V, which is the volume of distribution of urea, and here we use W, which is post-dialysis weight. We use W if V cannot be estimated. V usually can be assumed to be 55% of the weight. But actually, we can calculate the volume of distribution of urea very easy. But again, no one will use this formula or study this formula. We will use the online calculator that I will mention for you. An important point, if the patient has residual kidney function, this will add on the KT over V. So you have to calculate the residual kidney function of the patient and add it on the single pool KT over V through these equations. So here you will calculate first single pool KT over V, and then you calculate the total combined KT over V. Single pool KT over V, you have to add on it the residual kidney function of the patient. If the patient is dialyzing, has residual kidney function and is dialyzing for 3 times per week, use this equation. And if dialyzing for 2 times per week, use this equation. How to measure the residual kidney function, I will mention this at the end of the lecture. Again, these formulas and the calculators, you will find them on the calculator I mentioned before. And for example, this is our patient Mr. that we calculated for him the normalized protein catabolic rate at the beginning of the lecture. The same calculator will give you the single pool KT over V of the patient, which is here 1.62. And this patient residual kidney function is 0. If you added here the residual kidney function, if the patient has residual kidney function, that I'll mention later how to measure, we will find the single pool KT over V number will be changed and it will be higher. Okay, important points on how to collect blood urea sampling for calculation of KT over V. And these instructions will be used for blood urea sampling for every equation used for measuring of delivered KT over V. First of all, for pre-dialysis blood urea sampling, if the patient is using arteriovenous fistula or graft, take the sample from the access needle before beginning of dialysis session, before connecting the patient to the hemodialysis machine. If the patient is using a catheter for hemodialysis, venous catheter, discard the first 10 ml of blood from the catheter hub, then take the sample. Regarding the post-dialysis blood urea sampling, if you are sampling from fistula or graft, there are 3 ways. Well, the most commonly way is the first way, the first method. First, set up the ultrafiltration rate to 0 and decrease the blood pump speed to 50 ml per minute for a minimum of 10 seconds. And I will mention now why we have to decrease the blood pump. Then following decreasing the pump speed to 50 ml for 10 seconds, following this, stop the blood pump and collect the blood sample within the next 20 seconds. Why we have to decrease the blood pump? Slowing the blood pump is important to reduce the effect of cardiopulmonary circulation and the AVF access recirculation. Regarding cardiopulmonary recirculation, what is cardiopulmonary recirculation and how it may affect urea sampling? I will discuss this in the following slides in this lecture, when we talk about factors affecting solute removal and KT over V. So cardiopulmonary circulation I will discuss later in this lecture. Regarding AVF access recirculation and how it affects urea level in the blood, this will be discussed later in chapter 10, but as a short notice from here, what is access recirculation? Normally, if this is the arterial needle, the blood go to the dialyzer through the arterial line, then the blood comes back to the patient through the venous line and the blood goes to the patient body. But in some situation, some of the blood, the clean blood coming from the venous line, recirculates again into the arterial blood. So we are rewashing the blood again. What are the causes of this access recirculation? We will mention these details later in chapter 10, but this will affect the urea level while we are sampling, because rewashing of the blood will give a sample of blood with a very low level of urea. which will overestimate the KT over V. So slowing the blood to 50 ml here will decrease the rate of recirculation and allows accumulation of urea, which will give more accurate blood urea level by cancelling this effect of recirculation. The second method is to set also the ultrafiltration to 0, decrease the blood pump to 100 ml per minute, wait for 15 to 30 seconds, and then collect the sample from the arterial line. The third method and the least used method is to pause the flow of dialysate while maintaining the blood pump rate. After waiting a period of 3 minutes, withdraw blood sample from any point within the circuit. These methods are used if you are taking your sample from AVF or AV graft. But if you are taking your sample from venous catheter, take the sample from venous catheter after 30 seconds of slowing the blood pump. Slow the blood pump to 50 or 100. Again, why we are slowing the blood pump in the venous catheter? This is because we are afraid of what is called the catheter recirculation. We mentioned above in the I will draw. We mentioned here we are slowing the blood pump because we are afraid of 2 points: cardiopulmonary recirculation and access recirculation. Here in the catheter, we are afraid only from access recirculation, catheter recirculation. Cardiopulmonary recirculation is not common to happen in cases of catheter, and I will discuss later what is cardiopulmonary recirculation. We are afraid only here from catheter recirculation. What is catheter recirculation? Suppose it is the same idea as AV access recirculation, that if we have, this is the arterial line and this is the venous line of the catheter, that some of the blood is going out from the catheter. It is supposed that this blood will go to the patient body. We are afraid that some of this blood is recirculating and re-enter the catheter again and redialyzed. For example, if there is obstruction distal to the catheter, you may find this recirculation. That's why we decrease the blood pump in the case of catheter, to decrease the probability of this recirculation. So we discussed now the single pole KT over V, and we mentioned that the main pitfall of this single pole KT over V, that it neglects the idea that we have two pools affecting the serum urea level post-dialysis. The second delivered KT over V method is the equilibrated KT over V urea. The equilibrated KT over V urea, we call it two-pool or multi-pool, and it is clear from its name that it will be based on measuring the blood urea sample 30 to 60 minutes post-dialysis. So this method depends on the idea that we have two pools affecting the serum urea level. That's why the EKT over V, the equilibrated, will be lower than single pool KT over V, because single pool KT over V will measure the blood urea sample post-dialysis, which is in this example 25, but the equilibrated here, the blood urea sample is 40, higher blood urea level. So the dose of hemodialysis, if it is measured by EKT over V, will be lower than that in single pool KT over V. We have multiple formulas to measure equilibrated KT over V. The first one is to wait 30 to 60 minutes after dialysis and take blood sample from here, and then use the same equations we used in single pool KT over V. Here we used these equations to measure single KT over V, single pool. We will replace this by equilibrated KT over V. So you will take sample 30 to 60 minutes after dialysis and use the same equations of single pool KT over V. But it is impractical actually to wait 30 minutes post-dialysis, because your patient want to go to home, you want to disinfect the dialysis station for the coming new patients, so it is impractical to wait 30 minutes post blood urea. That's why Professor Dugirdes made a modified formula can be used to predict the rebound increase in urea post-dialysis after taking a blood sample immediately post-dialysis. So you will take to measure equilibrated KT/V, you just take immediately post-dialysis serum urine and use this equation. This equation is modified to predict the rebound and the serum urea level 30 to 60 minutes after the dialysis and give you correct ET/V, KT/V, which depends on the two pools IV. So you have to wait 30 to 60 minutes and use the same equations of single pool KT/V, or take a blood sample immediately post-dialysis and use this equation that is designed to, depending on the urea kinetic modeling, to predict the elevation or rebound of urea and correct the equation to get a accurate EKT/V. Again, don't forget to add residual kidney function for your EKT/V if the patient has residual kidney function, and you will use here the same residual kidney function equations we used in single pool KT/V, but just replace single pool KT/V by the EKT/V value you got. Again, all of these equations are available at the same calculator I mentioned. This is our same patient, Mr. But the same data you enter, just you press calculate. Here you will find that the equilibrated KT/V of the patient is calculated, which is 1.43. Again, the blood urea sampling precautions here to calculate the pre-urea level, the pre-urea sample and the post-urea sample. The precautions to these collections are the same as the precautions we mentioned before in the single pool KT/V, that you have to slow the blood pump and etc. We will go now for the third method to calculate delivered KT/V, which is standard KT/V rate. In the single pool KT/V and equilibrated KT/V, we measured the hemodialysis dose for one hemodialysis session. But in standard KT/V urea, we measure the hemodialysis dose for 1 week of dialysis treatments, whatever the number of dialysis treatments the patient had. So this is a collection of all hemodialysis treatment through the week. So if the patient had 3 dialysis sessions per the week, you could standard KT/V measures the hemodialysis adequacy for all the 3 sessions all over. The idea here, why we need this? Why we need to calculate the hemodialysis dose for all the week? This is because nowadays it is popular in some areas to have what is called frequent dialysis. The patient may be dialyzed more than 3 times per week. So if you measure the single pool KT/V or equilibrated KT/V for one session, this will not truly reflect the correct dose of frequent dialysis, because, for example, if the patient is dialyzing 5 times per week, so if you are calculating today the single pool or equilibrated KT/V for this patient, and you measure the pre-urea level, it will be very low, because the patient already had a hemodialysis session the day before. And for sure, the post-urea also will be very low. This may overestimate the KT/V. So it is recommended now, for example, by the European Best Practice Guidelines, if the patient is dialyzing 3 times per week, to use AKT over V, and in some guidelines mentioned to use single pool KT over V, but I will mention this later. But for hemodialysis schedules other than 3 times weekly, you have to use standard KT over V. A lot of formulas are available for the measure of standard KT over V. This is one of them. And don't forget, we have to add residual kidney function. This is the very complicated equation to measure to add the residual kidney function in case of standard KT over V. This equation is here, but again, the online calculator by Duberdes will give you the standard KT over V for the patient from the same data you entered, and this is very easy. So we finished now deliver the KT over V of the patient and how to measure single pool calibrated KT over V, which measure the dialysis dose for one hemodialysis session, and we mentioned and discussed the standard KT over V, which measures the adequacy of the hemodialysis sessions all over the week. So now we mentioned the prescribed KT over V, which is the KT over V mentioned by the manufacturer, the delivered KT over V, which is the actual KT over V in the patient, and it is lower than the prescribed KT over V, and now the online KT over V. Some hemodialysis machines equipped by a software called online monitoring, OCM, online clearance monitoring, or DIASCAN. This hemodialysis machine itself can measure the concentration of small molecular weights in the spent dialysate and can give you an estimated KT over V without the need of any blood sampling from the patient. But it is important to know that online KT over V urea must not replace the regular assessment of the delivered KT over V by the methods we mentioned before, as the single pool, equilibrated, or standard KT over V. Why? This is a study I didn't mention in my book. They measured or took the OCM, the online KT over V, of a patient through 8 weeks. This is the KT over V measured by the machine, and compared it with the KT over V, the actual delivered KT over V of the patient. Actually, there is difference between both of them. So the online KT over V can give you a rough estimate about the KT over V of the patient, but it must not replace the regular assessment and the measuring of KT over V. The last point to measure KT over V urea is the formal urea kinetic modeling. Actually, the formal urea kinetic modeling was suggested and recommended by the Kiduki guidelines for hemodialysis adequacy in update 2000. But actually, this method is very complicated. And by the way, it is not mentioned again by any guidelines after 2000, as it is very complicated and need complicated software, and it is largely unavailable, so usually it is not used. I wrote in my book some details about it, but actually it is not used nowadays, and it is unavailable. Now we discussed in details how to measure and calculate KT over V by different methods, but we didn't finish discussion about KT over V yet. We have to cover these points about KT over V: the recommended KT over V target, limitations, factors affecting and causes of low KT over V. Let's start by first point. We now know how to calculate KT over V, but what is the recommended target of KT over V? First of all, KT over V, delivered KT over V, I am talking now about delivered KT over V, should be done at least monthly. First, I will mention the recommended KT over V values in patients with no residual kidney function, zero residual kidney function. We have different guidelines. Regarding guidelines using single pool KT over V, the KDUKI guidelines in 2015 mentioned that if you are using single pool KT over V, the minimum delivered single pool KT over V must be 1.2 and your target must be 1.4. Regarding guidelines using the equilibrated KT over V, the European Best Practice Guidelines recommends that in patients who are dialyzing 3 times per week to have at least equilibrated KT over V by 1.2. The Renal Association Practice Guidelines said the same. For patients with thrice weekly dialysis, equilibrated KT over V must be at least 1.2. Regarding the standard KT over V urea target, which measures the dialysis dose for all the week sessions, the KDUKI guidelines in 2015 recommends a minimum standard KT over V of 2.1 and the target must be 2.3, but the minimum must be 2.1. These targets are for patients with no residual kidney function. But for patients with residual kidney function, the KDUKI guidelines recommends single pool KT over V targets to be as the following. Again, I will mention at the end of the lecture how to measure the residual kidney function. But if you measure the residual kidney function and the patient has residual kidney function less than 2 ml per minute, the targets will be different if the patient has residual kidney function more than 2 ml per minute. If the patient is dialyzing 2 times per week and has residual kidney function less than 2 ml per minute, there is no recommendation by KDUKI. If more than 3 ml per minute, if it is less than 3, there is no recommendation. If it is more than 3, the residual kidney function, the recommended single pool KT over V must be 2. If 3 weeks, here will be 1.2, here will be 0.9, 4 weeks 0.8, 0.6, and finally 6 times per week 0.5.4. You will find always, if the patient has high residual kidney function, the recommended single pool KT over V of the dialysis is lower than if the residual kidney function is lower. Let's say, see here 1.2, 0.9. This lower than this, and this lower than this. Why? Because the patient here has a good residual kidney function, which will compensate the hemodialysis. An important point here that the values, these values of single pool KT over V, recommended values here, are corresponding to a weekly standard KT over V urea value of 2. So if you reach these targets, it is equivalent that you have a weekly standard KT over V of about 2. Second point that I want to cover is limitations of KT over V. We mentioned from the start that although KT over V urea is the most widely used method to calculate the hemodialysis dose, but it has a lot of limitations. The first, that KT over V ratio was established in era where the most common dialysis patients are of younger age, with fewer comorbidities and diseases. But the current hemodialysis patients become older with multiple comorbidities. The second point is that the KT over V emerged during the use of cellulose dialyzers, which has a limited surface area and narrow pores. Now we have high flux dialyzers with large surface area and wide pores. KT over V depends on the kinetics of only urea. And sure, urea clearance may not reflect the kinetic physical criteria of other uremic toxins. Also from the limitations that measurement of KT over V, but this is away from standard KT over V. I am talking about a single pool and equilibrated KT over V. Doesn't consider missed treatments for dialysis sessions or dialysis sessions that are shortened due to any reason. The next point, that Kt over V may overestimate the dose in small-sized patient and malnourished patient, because these patients will have low V here, low volume of distribution. And finally, Kt over V doesn't consider other factors that are linked to patient outcome, as volume control, hemodynamic instability, or alteration in other biochemical markers. Now we have to discuss what are the factors that may affect solute clearance, and for sure this will affect Kt over V. Many points. The first of them is effect of blood flow rate. For sure, the increase in the blood flow rate will increase the clearance. We mentioned this figure before in one of our previous lectures, that there is direct proportion between the blood flow and the clearance, but the relation between them is not linear. We have some plateau at the end. The usual blood flow range is from 200 to 500 blood flow rate, in median about 350 ml per minute. So for example, if the dialyzer inlet of blood urea is 100 and the out blood urea is 40, let's draw it. If this is the dialyzer, if the blood urea entering is 100 and the outflow is 400 and the blood flow is 100, okay, so we cleared about 60 milli of blood is cleared from urea. If we increase the blood flow from 100 to 100, theoretically we will clear, instead of 60 milli, we will clear 120 milli. I want to mention that the relation is directly proportional, but again, at the end, it is not linear. Okay. The second point that may affect the dialysate flow rate is affect the solid clearance is the dialysate flow rate. For sure, increase in the dialysate flow rate will increase the clearance, but to what extent? This diagram shows the relation between blood flow rate again and the clearance. With increased blood flow rate, the clearance increases, but we have different lines with different colors depending on the dialysate flow rate. The blue line if the dialysate flow rate is 800, and so on. First of all, what is the optimum dialysate flow rate? Actually, the ideal dialysate flow rate is 1.5 to 2 times the blood flow rate. For example, if you have a blood flow rate of 250, so the ideal is 500, and so on. But the usual dialysate flow rate used is 500. So why not to increase dialysate flow rate more than 500? If I increase the blood flow rate to 350, so it is better, logically it is better to increase the dialysate flow rate from 500 to 700, as I mentioned, that the blood flow rate and the dialysate flow rate relation, that the dialysate flow rate is about 1.5 to 2 times the blood flow rate. I will tell you. Check here the curve of the dialysate 800 and the dialysate 500. Check the difference between them. At a blood flow rate of 200, there is no difference in clearance if I used a dialysate of 800 or 500. And check here at 350 blood flow rate. Again, the clearance between 800 and the 500 dialysate flow rate is not that much. The urea clearance increased only from 5 to 8%. And this is not that much to increase the dialysate flow rate from 500 to 800 and loss a lot of water during the hemodialysis session. So again, increasing the dialysate flow rate will increase the clearance, but again, the relation between them is not linear. There is a plateau at the end. And there is no much increase in clearance between the dialysate flow rate of 800 and 500. The next factor that may affect the solid clearance is the membrane efficiency, and we mentioned and discussed that in details before in the lecture of dialyzers. And we mentioned that we have low efficiency dialyzers, high efficiency dialyzers, according to mass transfer coefficient area less than 500 or more than 600. The second point can affect the dialyzer. The solid clearance is the clotting of the dialyzer. These are the different stages of dialyzer clotting, and for sure, the dialyzer is clotted, the dialyzer clearance of solute will decrease. The next point can affect the solute clearance is the duration of dialysis. For sure, shorter duration of hemodialysis sessions will decrease solute clearance. And if the hemodialysis session is interrupted due to any reason, for example, recurrent alarms, recurrent hypotensive episodes of the patient, this will affect solute clearance. The next and important point that can affect solute clearance is the effect of erythrocytes or hematocrit on solute clearance. Let's talk about urea equilibration between plasma and the erythrocyte due to hemodialysis session. If this is the dialysate, this is the plasma in the filter and RBCs in the filter. Urea moves according to concentration gradient during hemodialysis from the plasma to dialysate. Then urea will equilibrate as it will move from the RBCs again to the plasma, and then from the plasma to the dialysate. So urea movement away from the erythrocytes is very easy and very rapid. So any increase in the RBCs amount will not affect the urea clearance, because urea can move out from the RBCs rapidly and then to the dialysate. But the problem will appear in molecules where their outflux across the erythrocyte is slow, as creatinine and phosphorus. Their outflux from the RBC is low and very slow. That's why if there is increase in RBC's amount, erythrocyte or hematocrit value, a lot of creatinine and phosphorus will be within the RBCs, and their movement out of the RBCs will be slow and their clearance will be low during the hemodialysis session. The next point is the effect of solute distribution on clearance. Solutes, which are mainly intracellular as phosphate, their clearance from the plasma is rapid without significant overall removal from the body. How? Let's say this is the cells, not RBCs, the cells of the body, which have phosphorus in high value. And this is the blood. The phosphorus in the blood, the phosphate in the blood will be dialyzed easily, and the plasma level of phosphate will be cleared very rapidly. But the efflux of the phosphate from the cells to the blood is low. So after the hemodialysis session is finished, the plasma in the blood is very low, but there is high level of phosphate inside the body. That's why the overall body phosphate doesn't increase. And that's why dialysis alone is not enough to control the phosphate level in the body. Because after hemodialysis session, this phosphate will go out into the blood and elevate the blood phosphate level again. That's why control by drugs and diet is very important in hemodialysis patient to control phosphate level. Or another option to control phosphate by dialysis is to have frequent dialysis sessions or increase the duration of the dialysis session. This same issue is present in potassium ions. If you have a patient with hyperkalemia and you dialyze the patient because of hyperkalemia, you correct the potassium in the plasma, but the potassium in the cells is still high, and it will efflux into the blood, causing rebound hyperkalemia. That's why in hyperkalemic patients, it is important to hospitalize them after hemodialysis, because there is a possibility of this rebound hyperkalemia, and you may re-dialyze the patient again. The next point affecting solute clearance is accessory circulation, and we mentioned that earlier, and again we mentioned that in chapter 10. This recirculation will cause clear blood to re-enter in the dialyzer and decreasing the inflow of blood having a high level of urea, and this will affect the dialysis adequacy and dialysis dose. And we will talk about this later in chapter 10 in details. Now, what about cardiopulmonary circulation that we mentioned before? Cardiopulmonary circulation, and also it is called arteriovenous disequilibrium. What is cardiopulmonary circulation and how it can affect the dialysis adequacy? Let's say this is the tissue, and this is the arterial blood going through the tissue, and this is the blood coming out from the tissue in the peripheral veins, and it contains a high urea concentration. This is the axis arm, this is the arteriovenous fistula, and here it's a connection with the hemodialysis machine. The blood coming from the hemodialysis axis, this dialyzed the blood with a very low urea concentration. Both the blood coming from the tissues with high urea and the blood coming from the axis with low urea concentration will mix in the central veins. So the central veins contain blood coming from tissues and the blood coming from the axis. This is with high urea level and this is with low urea level. So the central veins blood is diluted with lower urea concentration than peripheral veins. The urea concentration here in the central veins will be lower than that in the peripheral veins. This low urea concentration blood will go to the heart, and then again it will go to the vascular axis. So the blood coming out of the heart is diluted with low urea concentration. It will go to the axis. So the blood entering the axis is already diluted and contains low urea concentration. So if I took a blood sample from here for urea, the urea level will be low, and this will overestimate the Kt over V. That's why we mentioned if you are taking a sample here, you have to decrease the blood pump to 50. Why to decrease the blood pump to 50? To decrease the effect of this, to decrease the clearance of urea, and this will decrease the effect of this cardiopulmonary circulation and this dilution, making a slower blood, slowing pump, decrease the urea clearance, increase the urea level in the veins, increasing the urea level in the blood coming to the AV axis. So this is the cardiopulmonary circulation, and it has an effect if we are using AV axis. But if you are using a venous catheter, the cardiopulmonary circulation usually has no effect. This is the tissue, and this is the blood coming from the tissue with high concentration going to the central veins. The venous catheter is inserted in the central veins. So you will take blood with high urea concentration coming from the tissues. Then, yes, for sure, the blood coming here from the catheter is with low urea concentration. But this blood will go to the tissues and then come out again from the tissue with high urea concentration. So the blood coming to the venous catheter, if you draw a blood from the venous catheter, it will has high urea concentration. Let's complete the picture. Where is the fistula? If we are using a fistula, the fistula is here. Let's suppose this is the arm of the patient, this is the fistula. The fistula is taking blood from here. So the blood, if this is a diluted blood with low urea, this diluted blood with low urea will go to the fistula. So the blood in the fistula is with low urea concentration. But the blood going to, because fistula take its blood from the arterial system, while catheters take their blood from veins. So the blood here, which is diluted coming through the tissues, will go to the catheter with high urea level. So cardiopulmonary circulation has no effect on venous catheter, but has effect on arteriovenous fistula and graft. From all what we mentioned, let's collect in few points what are the causes of low Kt over V. First point that may cause low dialysis dose is low blood flow rate. The second is low dialysate flow rate. The third, if the dialyzer is clotted. Short duration of dialysis sessions, whatever the cause. Access recirculation. And finally, if there is error in blood sampling and you didn't follow the steps that we mentioned in how to sample urea from the patients. Now, finally, we covered the first part of measuring hemodialysis dose, which is KT over V urea. Other methods rather than KT over V urea that can be used to measure hemodialysis dose, but actually they are not recommended. They are not recommended. The first is the urea reduction ratio. The urea reduction ratio, we measure how much urea, or what is the percentage of urea clearance throughout the dialysis. You measure the pre-dialysis bone concentration and post-dialysis and divide this by pre-dialysis blood urea concentration to get the percentage. The accepted percentage of urea reduction, how much urea is reduced for the hemodialysis session, is 65% or higher. For sure, the pitfall of this is that we only depends on urea here. Urea clearance only. We doesn't include in this ratio the duration of dialysis, volume of ultrafiltration, volume of distribution, and so on. That's why urea reduction ratio is not recommended to be used. The second point is solute removal index. In this part, they collect the dialysate spent through dialysis, and they measure the urea concentration in the dialysate and multiply it by the volume spent dialysate. But actually, this is not practical to collect the spent out dialysate. We are talking about 120 to 200 liter. How I will calculate 120 to 200 liter from the patient to measure the urea concentration in them and to know the volume of spent dialysate? This is not practical. So the limitation of this method is that few studies have correlated patient outcome with this method. And the second point, that collecting the outflow dialysate is not practical at all. And finally, the solute removal index is relatively inaccurate when it is compared to the equilibrated KT over V. Nowadays, there are some machines that calculate solute removal index online. They calculate the spent dialysate. You are not in need to collect the spent dialysate. By the machine, calculate the amount of the spent dialysate and measure the urea concentration in it, and gives you directly the online measurement of solute removal index. But again, away from collection of the outflow dialysate, there are a lot of limitations for this method. Finally, how to calculate residual kidney function, that we have to add to KT over V whenever it is present. Residual kidney function is the remaining ability of the diseased kidney to excrete water. Some of your patients, water and toxins. Some of your patients may start hemodialysis with a good residual kidney function, or its better name, residual urea clearance. And there is evidence that the preservation of this residual kidney function for a longer time is sufficient to significantly improve overall uremic control and reduce the need of hemodialysis treatment. But it is important to mention that changing dialysis time or frequency is not recommended based on residual kidney function, except if you are measuring residual kidney function at least monthly. So if you will decide that I will increase or decrease the patient hemodialysis sessions depending on the residual kidney function, you must not take it roughly. You have to measure it at least monthly, because unexpectedly the residual kidney function may be reduced. How to calculate KT over V? First of all, this is the first dialysis session. After the session, you have to take post-dialysis blood urea, and we will call this blood urea nitrogen 1. And at this point, the patient must empty his bladder, and this urine is discarded. The patient must empty his bladder in your unit. Okay. Then this is the second hemodialysis session. between the first hemodialysis session after the patient discarded the urine from the bladder, and between the two sessions, the patient must collect all the urine volume. Then before the next session, you have to collect pre-dialysis blood urea, and we will call this blood urea nitrogen 2. Now you have blood urea nitrogen 1 immediately after the first session, blood urea nitrogen 2 immediately before the second session, and all the urine volume here is collected, and you will measure the urea concentration in this urine. So you have the volume of urea, the volume of the urine and the urea concentration in this urine. Then you will use this equation, and again there is available calculator that I put in my book to measure automatically the residual kidney function. You have to put here the data. Again, here the intradiuretic urine volume, the urea concentration in the urine, intradialytic period, which is the time difference between dialysis 1 and dialysis 2, blood urea nitrogen 1 and 2, and so on. Finally, we finished this important lecture. I hope that it was clear. And the next one, inshallah, will be lecture 7 about anticoagulation for hemodialysis procedure. Thank you.